Hello everyone, welcome to the Introduction to Mechanical and Industrial Engineering course, MEC 130. This is part 4 of the mechanical design. In this part, we are going to discuss stresses, tensile stress, engineering materials, and dynamics, and factor of safety. Over the last part, or the previous part, we discussed the unit cell, the unit systems, and conversions, and the force analysis. But these are the topics that will be covered in the part 4. Alright, so as we discussed over the previous videos, we introduced the forces that would act on or between the different mechanical components that would be used for making a machine. This machine contains so many components, and definitely there are some forces, as like the case of the forces that would be generated between two gears, that one will enforce the other one to rotate. So there should be some forces generated between these two mechanical components. And we said that this force, it is something hidden, it is not seen, but we can feel and observe its effect. We cannot see the force, but we can see the effect of that force. So simply when a solid part, whatever it is subjected to a force, it would be either deform or move. It means that the force in general should do something to this mechanical component, should do something to this solid part. This something could be in the form of deformation or movement. Like if you have a box and you try to push this box is going to move. So this is one of the reasons, one of the responses of this object to the applied force. One of the causes of the force, one of the results of the force. Like you have an object, and you're gonna apply a force on this object, so this object, it would either deform or move or do both of them. Either to do just deformation or just motion, or both deformation and motion, and we are going to explain this in details. So if the object is constrained to move, it will deform up on a force acting on it. So what is deformation? What is motion? To explain it, let us consider that you have a box. And this box is sitting on the ground, and nothing prevents this box from movement. So if you try to apply a force, like a push, over this box definitely it will move. So there is a motion or movement that is going to produce because of the applied force. When this box, it should be moved in case that there is no constraints, there is nothing that would stop this box from movement upon applying a force on it. So it means that there are no constraints that would prevent the box from movement. So in that case, the box will move. This movement, it is a reason, it is a result. It is a response known as the response of the box to the applied force. Like you have this box with a certain mass, with a certain specifications. So when you apply a force on it, it's going to move with a certain velocity, displacement, and acceleration that depend on both the force and the specifications of this box. The characteristics of this box, the weight of this box, the mass, the size, the shape. All of these details are located as specifications of this box that is subjected to a certain force. So as a response, as a result of this force, this box is going to move with a certain displacement, velocity, and acceleration. So the response, it could be in the form of motion. But how about for some reason, if we just put or build a wall, a very strong wall in front of the box, and you try to push it, do you think it's going to push or move? No. In that case, there is no movement, but instead, this box, it will start to deform. Deform, it means that it's going to change the shape of the box. Assume that this box, it is kind of rubbery material. It is made of plastic, made of a rubber that is deformable, that it can be bended, stretched, and with no problem. So if you try to push it or apply a force over this box against the wall, it won't gonna move because there is no space, there is no room for this box to move. So there is no movement, but instead, the force should do something. The force, if this box, if nothing gonna happen or a change to this box in terms of movement, in terms of a change of the shape, it means that definitely there shouldn't be any force. But since we are applying a force, the force should do something, should do changes to this box. Whatever a change in place, as a movement or a change in the shape. So the change in the shape of the box, assume as I mentioned it is made of plastic, so it's going to deform. Assume that it's going to take or attain another shape because of the pushing against the wall, so it will take another form, another shape. So the new shape or the difference between the new shape of this box and the original shape without the force, this is known as deformation. This indicates that something happened to this box because of the force, but this something is known as deformation. So generally speaking, the force should do something to any object. This something, it could be in the form of movement or deformation, which is related to change of the shape of that object, or both of them. You may have an object that is going to move, plus it's going to deform. So these are the two results. Either one of them, either deformation or movement, or both of them consequently going to act over this object. Deformation, just to explain, let us assume this ball, spherical ball, and you, for some reason, you're just going to apply a force on it by your bare hands. Assume that it is made of plastic. This is like the regular pore, so it's going to deform, no problem, right? Deform, it means that it's going to attain another shape. It has like this perfect circular shape or perfect spherical shape. Now it's going to have elliptical shape. It's going to have an ellipse. It means that there is something that is happened to the shape. The shape would change because of the applied force. It means that we can describe or mention that this force resulted in a deformation into this spherical ball. And this deformation, it could be permanent or it would be temporary. Permanent, it means it will be forever. It will not change even if we removed the force. So initially we're just going to apply some force over this object, so it's going to deform, it's going to change the shape, it's going to attain a new shape. Once we remove your hand, there are two options. This object, it could have the capability to restore back again to the original shape before the force. So there is no force here for this case. And once you apply the force, it's going to have this elliptical shape. How about if I decided to remove the force, cancel the force, remove your hands of this ball. So what's going to happen? This ball, it will restore back again to its original and perfect circular shape. So it means that this deformation was instantaneous. Deformation was temporary. It wasn't permanent deformation. In some other scenarios, how about if this is not made of plastic, this is spherical board, but instead it's made of clay, or made of slime, or made of a Play-Doh, for example, that's these things that the children are using. So simply if you apply a force on it, it will not, and then you remove your hand, it will attain a new shape, and this shape will be permanent. It will not be restored back again. So the deformation in general, it could be permanent deformation because of the force. You're going to apply some force, and the object will attain a new shape or will exhibit some deformation, and this deformation will be permanent. The other scenario, it could be temporary. Temporary, it means that instantaneous, at the instant that you apply a force, there is a deformation. Once you remove the force, the deformation will be eliminated. The object will restore back again to the original shape. Make sense? The same thing if you have a stick or bar like this one and using your bare hands and you try to bend it. Bending, as we mentioned in the previous videos, bending is something that gives deformation or gives rotation to objects. Like when you're handling this bar and you try to rotate your finger this way, you just definitely gonna end up with a little bit bend into this bar as already given here. So before deformation, before the moment, before the force, because the moment it is related to the force, it is the indirect effect of the force, as we mentioned. So this bar was straight. Upon applying a moment over this bar, it will be bended, it will be curved, have this curvature. It means that there is a change in the shape. This change in the shape, it is a slight change, yes, because you're going to have a slight bend into this bar, no problem, but it is a change in the shape. It was straight, now it is curved. So there is a difference in the shape. This difference, it is measured by deformation. This is an indication that there is a deformation that is happening into this bar because of the moment. The reason is the moment. Once you remove the moment, you'd have two options. One option is that this bar can restore back again to be straight one more time once you remove the moment, and in that case we're gonna say that this deformation, it is a temporary deformation. It is not a permanent one. But the other option, how about if we remove our hands and instead this bar will keep curved without, and it will not restore the original position or to be straight one more time. This means that this deformation will be a permanent deformation. As we mentioned, the deformation in general, it is a change in the shape of the object, that it could be permanent or temporary. Depending on what? Depending on lots of things. One of the things is the material type of this bar. As I mentioned, in case that this ball is made of plastic, so it is most likely that this deformation is going to be temporary deformation. It means that it will restore back again. But if it is made of clay, it will not restore back again to its original shape. Make sense? So this definitely depends on so many things. One of the things is the material type of this object. And that's why, as a part of this part, or discussion on the part 4 of mechanical design, we are going to discuss the different types of material that we are using as engineers. Make sense? So deformation, it is a kind of a change. So we can generally define a deformation as it is any change in the shape. So it is a kind of a change in the shape and or dimensions of the part up on or due to an applied force acting on it. Like you do have an object that is subjected to some forces. This object could change some of its shape because of the force. How we can measure how severely this object is affected by the force, this can be measured by the deformation. How much of a change in the shape that this object gonna exhibit or experience because of the applied force, this is known as the deformation. So simply the deformation, it is the change or it is a measure of the change in the shape or the dimension. It is not necessary to be change in the shape. It could be that changes in the dimensions. Anyway, it will be counted as deformation of the solid bar due to an applied force acting on it. The deformation can be determined by as an elongation. This is one of the forms, one of the examples. There are lots of forms and types of deformations. The simplest type that you have this rod or this stick, and for some reason that you are going to apply a tensile force. Tensile force, it means that you're just gonna try to stretch this bar. So once you apply a force, this bar is going to elongate. It's going to increase the length of this bar because of the applied force, as already shown here in these two diagrams. Like this is the bar with an original length L, and up on applying some forces, it will be stretched. So this delta, this is the difference between the original length and the new length after the force. So the original length without the force, it was L. Up on applying some force, it will be elongated. So it will attain a new length. Let us name it like LN. N stands for new length. So the difference between L new and L original, this is gonna give us delta. So this symbol is mentioned as delta. So this delta, it is a measure. This is the deformation. This delta, it is the deformation, which is measured as elongation into the bar when it is subjected to a tensile force. So the deformation can be determined or measured as an elongation in a bar under a tensile force. Or it could be in other form, because as I mentioned, this is the simplest forms to understand what is a deformation. Here, this delta, it represents the change in one dimension. A change in the length. The length was L, now it became Ln. So the difference, this gives us delta. It means that there is a deformation, and this deformation is measured by elongation into this bar. Because of what? Because of the applied tensile force. The deformation by itself, it is not accurate measure of how a solid bar is severely affected by a force. So, and this introduces to us something that we're gonna name as a strain. So what does it mean, strain, and what is the difference between the strain and deformation? To understand this, let us consider these two examples. Assume that you have a bar here, and this bar is fixed to the wall, and for some reason we are applying a force P over this bar. And this bar is uniform. It means that assume that this diameter it is perfect diameter of this bar. The same thing for you to have a very similar bar that is made identical, made of the same material, having the same diameter, having the same dimensions. All the dimensions are the same except one dimension, that this length of this bar, it is 100 or let's say 10 millimeters, but this bar has a length of 100 millimeter. So again, and this one is subjected to another force, let's say like P2 and this is P1. So assume that you do have two bars having the same diameter. The diameter is the same, circular, and it is extended like a cylindrical shape, just bar. And this bar is fixed to the wall from this side, the same for the other bar. Both are made of the same material, but the only different thing is that the length of this bar, it is 10 millimeter, here it is 100 millimeter. But having the same material, the same diameter, and then they are subjected to two different forces. So P1, P2, these are forces, not pressures, these forces. So because of this force, we said that the force should do something to this bar, right? So because of this force, this first bar had been elongated and it will attain a new length that it should be longer, definitely. This new length, it became 105 millimeter. So what does it mean this? It means that because of this force, this bar have been elongated 5 millimeters. I'm sorry, not 5. This is 10, 15 millimeter, because this was 10. So it means that it had been elongated just 5 millimeter. How about the other bar? The other bar is going to do the same. It will be subjected to a force, but another force. We don't care about the amount of the force now, but in general, this bar has been elongated to attain a length of 105 millimeter. So if I ask you, according to our definition of the elongation delta, this delta, it should equal to the difference between the new length negative the original length, right? Because this delta, it is the difference of the new length negative the original length. So if I ask you to calculate the delta, which is a measure of deformation, this is the deformation as I mentioned. The deformation equals, it should equal to the new length, which is 15, negative the original length, which is 10. This gives us 5 millimeter of elongation. The same thing here. If I ask you to calculate the delta, it will equal to, which is deformation, it will equal to 105 negative 100 equals 5 millimeter. So what does it mean this? This means that this bar has been deformed by 5 millimeter, and this bar also had been deformed by the 5 millimeter. So the deformation in both bars are the same. But in fact, that this deformation, it is not an accurate measure of identifying how severely this bar is affected by the force. For example, what is the effect of this force over this bar? It will result in an elongation into this bar by 5 millimeter. This 5 millimeter, if you try to compare it to the 10 millimeter, it is a big deal. It is almost, you stretch the bar to half of its original length. It means that this bar, it is seriously, it is severely, it is very highly affected by this force. But how about on the other side? This 5 millimeter in comparison to the 100 millimeter original length of the bar, it is not a big deal, it is nothing. It is very small in comparison to this 5 millimeter with respect to the 10. It means that despite the deformation in both is the same. So if I ask you a question, what is the effect of this force over this bar and this force over this bar? Which one it will be affected the most? Which one will be affected higher than the other one because of the force? Which one is likely to be fractured first before the second one? If you consider the deformation as your reference, as a measure to judge whatever this one will be affected first or fractured first than the other one, affected most by the force than the other one, this measure it is not accurate. Why? Because in this example, in this case, we are getting the same deformation. So according to the deformation, both are affected to the force the same way. But this is not true. In truth, this bar, this short bar is the one that it should be fractured first than this one. Why? Because the 5 millimeter with respect to the 10 millimeter, with respect to the 10 millimeter, it is a big deal. But the 5 millimeter with respect to the 100, it is not a big deal. It means that this one is affected more than the other one. So the deformation, it is not the accurate measure to give us an idea how severely objects are affected by the applied forces. It is one measure, yes, that gives us how these objects are affected by the force or the changes in the dimensions of the shape of the object because of the applied force. But it is not the only measure. It is not the most accurate measure. Why? As in this example, there is no difference between these two objects if we consider the deformation, while in fact that this object it should be fractured before this one. This one is likely to be broken before this one. Why? Because the 5 with respect to, you have to compare. We knew this because we have to compare between, refer all the time to the original dimension. We had to refer to the original dimension. So referring to the or comparing to the original dimension, this 5 it is a big deal, but this 5 it is not a big deal. It is not big difference. So it means that this bar it will not be affected that much like this bar. This one is likely that this is the one that is going to be broken first if this should be happen before this one. Make sense? So it means that we need another measure, and this what defines this strain. So this strain, this is a more accurate measure than the deformation in identifying the importance or the effect of the force or describing the effect of the force over objects. This is strain that we're gonna give it a symbol epsilon, and we're gonna discuss this one. Epsilon, it will equal to the delta divided by L. That we are comparing the percent of the deformation with respect to the original length. L, this is the original length. So if I calculated the delta here, it will be 5 divided by 10, which is the original length. 5, which is still the deformation, but we are referring to the original length. This is gonna give us a half. But the strain here, it will equal to the delta divided by L equals delta, which is the deformation, divided by the original length, which is 100, which is gonna give us a small value, which is 0.05 millimeter. This is millimeter over millimeter, and we're gonna discuss the units. Okay, it means that if I ask you how much is the strain here, it will be 0.5, but here it is 0.05. This means that this bar will be subjected to a very small strain in comparison to this bar, which will be subjected to a very high strain. It means that this bar is the one that is going to fracture before this one. How did we know this? From the strain. The strain, we got different values of the strain. This strain is bigger than this one. It means that this one is strained more. It is stressed more, is likely to be fractured first before this one. So this indicates that the strain, it is a more accurate measure than the deformation. Why? Because the strain, it is the deformation in comparison to the original length. We have to refer to the original length so we can know exactly how severely these objects are affected by the force. So if we're gonna define the strain, and this is what distinguishes the deformation from the strain. The strain, it is a more accurate measure of how a solid part is severely affected by the force. It relates the deformation to the original shape or dimensions of the object that we have to relate to the original dimension. The deformation by itself, it is a measure of the changes in the shape or the dimension of a solid bar because of an applied force. This is what is deformation. But it is not accurate when compared to the strain. The strain is more accurate measure that gives us an idea how severely the object is affected by the force. And the strain, what is the strain? It is the deformation with respect to the original shape or dimension of the solid part. So that's why the strain, which is epsilon, this symbol is known as epsilon, this epsilon equals delta, which is the deformation divided by the original length. Make sense? So this is for the difference between the deformation and the strain. In addition to these two measures, deformation and strain, we do have a third measure, which is even more accurate than both of them. The strain, it is more accurate than the deformation. Why? Because we refer to the original dimensions. Going back again here, from the beginning, we assume that both are made of the same material, right? So, but how about if both are made of two different materials? This one is made of plastic, for example. This one is made of another material, wood, for example. So the material, it will have a role here. It means that the material will have a contribution. So depending on the material, one would be fractured than the other one. So, but if both are made of the same material, so there is no measure with respect to the material because both are identical in terms of the material type. So that's why in case that they had the same material, we said that the strain, it is a measure that can give us an idea who's gonna be fractured first. But how about if they are made of a different material? The material will have a contribution, and based on the strain, we said that this is going to fraction first, but this is not, it shouldn't be the case in case that both have two different materials. Probably this could be made of a very strong material. Yes, it is subjected to very high strain, yes, but its material, very, very strong material in comparison to this material. It is subjected to small strain, yes, but it is very weak. It is made of a very weak material. It means that this one is going to fracture first before the other one. So what does it mean this? In that case, the strain will not be the accurate measure to judge who's gonna be fractured, which part is gonna fracture first. In case that the material will be different, it means that we need another measure, a third measure that consider the material effect into account to judge who's gonna or which bar is gonna fracture first, or the influence of the force over this bar, which is the strain, the stress. So the strain should be related to the material. In some cases, as we mentioned, the strain, it couldn't be it may not be the accurate measure, because in some cases we need to refer to the material type, especially if we are comparing between two different material types. So it means that the strain should be related to the material type to give more insights into how a solid part is severely affected by a force or how it is stressed by the force. So this introduces the stress. The stress, it relates the strain to the material. So as you can see, it is like kind of sequence. The deformation, it is the change in the shape and dimensions, but it is not accurate in all cases. The strain, it is more accurate than the deformation. And what is the strain? It is the deformation referring to the original dimensions, original shape. But the strain in some other cases, it may not be accurate because that we need another measure that depends on the material. And this is what gives us the stress. So what is the stress? The stress, it is the strain related to the material type. So the strain is related, the deformation related to the original dimensions. The stress, it is the strain related to the material type. So the stress, it is a measure of the material deformation in relation to the material type. Material deformation or material strain. We can even replace this one to be more accurate, to be the strain. The material strain in relation to the material type of the solid part. Make sense? So it is the most accurate measure in general that could be used is the stress. So that's why in the mechanical design course, when we do design for any mechanical component, we are all once you do, as I mentioned in the previous videos, the first step is to do force analysis. Find the forces that acting over this part. Then the second step is to calculate the stresses. Why stresses? Because I would like to know how severely this mechanical component will be affected by the force. And the most accurate measure to measure how severely parts are affected by the force is the stress. The stress, consider everything. Consider the original dimensions, consider the material type into account. So that's why it is the more accurate. It is even more accurate than the strain and the deformation. So that's why in the mechanical design course, your calculation all the time will depend on the stresses. You barely calculate the strain or deformation. We don't care about them, especially the deformation, unless we would like to measure over the rigidity. This is another criteria that we are going to discuss shortly. But anyway, the main concern is the stress of this material that acting over this mechanical component because of the force. So the stress, it is a measure of the material strain or deformation relation to the material type of the solid part. How could the stress be related to the strain? Through the Hooke's law. This is the simplest case in case that you don't have a bar that is subjected to a normal stress, sigma. So this sigma, this is the measure of the stress. So again, just to know, I acknowledge the symbol. This delta refers to the deformation. This epsilon, this is known as epsilon. This epsilon, it is a measure of the strain. And this sigma, this is known as sigma. This sigma, it is the measure of the stress equals E, and I'm going to mention what is this E times epsilon. Epsilon, this is the strain, which is epsilon. Make sense? So what is E? This is known as the Young's modulus or the elastic modulus, and this is a material constant. So what is a material constant? Every material has its own elastic modulus. So it is like a signature to this material. Like for example, as of yourself, you do have your own name. You do have your stamp, finger stamp. So, or fingerprints. So the same thing, this is like a fingerprint of this material. Or this is like, for example, the signature of this material. It is a property. It is something that distinguishes one material from the other one. Every material has its own value for the Young's modulus. And this is the thing that relates the strain to the material type. As we mentioned, the stress, it relates the strain to the material type. So that's why we do have here E, which refers to the Young's modulus. There are more accurate or not accurate, more general form of this relation. This is known as constitutive relation or the stress-strain relation. But anyway, these other relations will be explained to you in more detail in the mechanics of material class. But we were not going to consider all of these details through this course. As I said, I just want to give you an overview, an idea ahead of time what you are going to study for the mechanics of material class. For the mechanics of material class, you're going to study with more detail how you can calculate these stresses, how could you relate them to the strains that would be acting over the object. Make sense? So that's why this is the simplest form that gives you an idea how the stress could be related to the strain through Hooke's law, which is sigma equals E times epsilon. Epsilon, this is the strain, sigma, this is the stress, E, this is the like a constant. This constant is known as the Young's modulus or the elastic modulus of the material, and it is a material property. What does it mean, a material property? It is something that distinguishes one material from another material. Copper, for example, has its own Young's modulus that is different than the aluminum. That is different than the Young's modulus of steel. That is different than the Young's modulus of any other material. Make sense? So it is a material property. Alright, so how the stress could be related to the strength of the material. So we should acknowledge the difference between these two keywords, stress and the strength of the material. We said that the stress, it is the more accurate measure that could relate the influence of the force to the material type. So the material type, it is measured by something that we name as strength, and the stress, it is something that is related to the applied force, because you could have a material. This material is subjected to a force. This force will produce some stresses which not seen. We cannot see these stresses or forces. It is something virtual, but we can measure their effect. We can observe their effect. So there is an effect of this force in the form of stress, and the stress is something here that we can observe over the material itself. The material, it has a measure which is strength. This strength, it is a material property. What does it mean, material property? It depends on the material type. Like the Young's modulus, we said that this Young's modulus, it would be different from one material to the other material. It is a material signature. It is a fingerprint of every material. The same thing, every material has its own strengths, has its own ability to support stresses. So what is the stress and how it could be, or the strengths and how it could be related to the stress? Let us consider this very simple trick or example of a stick. Like, you assume that I'm giving you a stick, and I'm gonna ask you to fracture this stick. Assume that it is made of wood. So initially, I'm just gonna give you a very thin stick, like the diameter of the stick, the circular diameter of this stick, it is too small. This here, I'm talking about the diameter, this one. The circular diameter of this stick, it is a small thing, very thin stick. Then I give it to you, and it is made of wood, and I ask you to fracture, just to break it. So it will be fractured, it will be it will be broken, right? Very simple. Once you bend it, it will be directly broken, no problem. But how about if I then give you more sticks, and as I give you one more stick, I'm increasing the diameter of the stick. This diameter is going to increase one by one. Like initially, I'm going to increase the diameter a little bit, then you can fracture it or break it. Then I'm going to give more thicker one. You still breaking it till you reach a certain diameter. Here I'm not changing the material. I'm still using, all the sticks are made of wood, made of the same material. But the only thing that I'm doing here, I'm just increasing the diameter of these sticks. At certain diameter, you will not be able to break it, right? Below this diameter, you can break the sticks. Any stick that is at this diameter or higher, definitely you will not be able to break it by your bare hands. So this depends on your strengths. This depends on your ability, how strong you are, you are capable to break it. So when you try to bend, you are applying moment. We said that this is kind of moment over this stick, so you can break it. It means that you can capable of producing a certain amount of stresses acting over this stick to break it. Initially, the stick was weak because the diameter was small. So as we increase the diameter, it became more stronger. So it means that till you reach a certain diameter, that you will not be able to break it anymore. You have a certain amount of stresses that you can produce over this bar to break it. You will not be able to increase the stress anymore. Make sense? So it means that the size or the diameter, which is related to the size of this stick, this one was thin, this one was thick, right? So the size, it is a big deal. The size, it do affect whatever we can break it or not. Another measure is the material. How about if I give you the thin stick that is made of wood, simply you can break it. How about if I replace this thin stick by a steel bar or stick? And instead of being made of wood, it will be made the same diameter. Yes, I didn't change the size, but I changed the material to be steel. And I ask you to break it. You will not be able to break it. You can the only thing that you can do, you can bend it. But it will not be completely split into two pieces, right? Why? Because I changed the material to a stronger material, to a different material, so it will not be breaked. It means that the material is another measure, is another thing that could be or affect the ability of your hand, your ability to break it or not. So from this trick or from this game, we can conclude that the ability of the stick to support a force depends on two things: its material type and the size. Initially, the stick, the thin stick, it fractured easy. It means that it is kind of weak. It is made of wood, yes, but it is kind of weak. Why? It has lower diameter and the material type, it is weak material. Wood, it is not that strong material. How about if I replace this stick by the steel? You will not be able to break it. Why? Because the steel is a strong material. So the material, it gives, as we are using more stronger material, we are giving more potential to this part to support stresses or forces. Also, as we increasing the diameter, we are giving more potential to this part or this stick or bar to support more forces. So generally speaking, we can say that the ability of any mechanical component, whatever it is, to support forces, and forces can somehow be converted into stresses, depending on what? Depending on two things: its material type and its size. So from this we can conclude that the strength, it describes the ability of a solid bar to support and withstand the stress applied to it. So for example, if you do have this mechanical component like this shaft, it is made of a certain material and it is made with a certain shape and size. So these two things gives this bar a certain ability to support the stress, gives it a strength to support the applied forces, and somehow we can convert these forces into stresses as I mentioned. So in case that the applied stress, which comes from the force, the stress, it is something that related to the force acting over the mechanical component. If it is bigger than the strength of this bar, the solid bar will be fractured, will be broken down. Why? Will fail. Because of what? Because the applied stress, you are applying a stress over this bar which exceeds its ability, exceeds its strength. So definitely it will be fractured like this shaft. This is a fracture shaft. This is the fracture surface. This surface has been broken from here. It was like very long shaft, and this is one piece. It had been broken into, split into two pieces. Why? Because we loaded it. We applied stresses over this shaft that exceeds its strength ability. So that's why it had been broken. But in case that the applied stress, it is lower than the strength of this part will work properly and it will work perfect with no fraction. So in order to design a mechanical component, we have to make sure that the stresses that acting over this component due to the force should be less than the strength of this shaft. This strength, it is well-known value that depend on the material type, and somehow there are some other measures that related to the size can be included in the factor of safety. But anyway, there is a specific strength to this shaft that we are pretty sure of it. We know this value. So we do have a certain limit. This is our maximum limit. We shouldn't load this shaft with a stress that is exceeding this limit, otherwise this shaft will be fractured. It is very similar to the elevator. When you use the elevator and you try to read the label that this is gonna give you a maximum capacity for the elevator. This maximum capacity, how did we define this capacity? Based on the stresses. Because we know that this elevator, the wires, because this elevator are using wires, the wire that move this elevator, they do have certain strength. So we calculated and we put a limit of the stress, that the stresses that acting over this wire shouldn't increase or exceed a certain limit. If it increases, these wires will be cut and definitely we're gonna end up with a disaster with this elevator. So the same thing here for any mechanical component, whatever it is. There is a maximum limit for the stress that it shouldn't all the time exceed the strength of this mechanical component, otherwise it will be fractured. So the strength, it is one of the design specifications. If you remember in the part 1 of mechanical design, we defined what is a design specification, and we said that in general, anything that limits the ability of or the freedom of the designer or the design engineer to design and select his design. So one of these design specifications is the strength, that this machine, this mechanical component should have or attain should have a certain strength. It means that you have to keep the stress lower than this strength value. The designer should find the suitable material, and this strength, as I mentioned, it is related to the material type and the size or the dimension. So your objective in the design calculation of a shaft, the design calculation of a gear, you are searching for two things. What is the suitable material that should be used for making this gear or shaft? What is the suitable dimensions of this shaft to support the forces or the stresses? So the designer should find the suitable material and dimension of the solid part to be strong enough to support or withstand an applied stress, and this is the objective of your objective to do while you are doing design for these mechanical components. Make sense? Alright, so now let us discuss the different types of stresses. Stresses in general, there are two types of stresses. There are two types of stresses only, nothing more. Either normal stress or shear stress. So the stresses are either normal or shear. This definitely will be explained to you with more detail in the mechanics of material. All these stresses and these different normal and shear stresses and how you can do lots of application and solve lots of problems related to this. This definitely is the objective of the mechanics of material class. Make 302 in your study plan, whatever you are, mechanical or industrial engineering. Make sense? So what is the normal stress? What is the shear stress? So the normal stress, forget about the definition because it needs so many details, so you could understand why we give it a name as normal stress. So I will not gonna go over this thing, but the important thing that you should understand how this normal stress is going to generate. There are three scenarios that would produce a normal stress, nothing more, three options. The tension to a bar, assume that you do have a bar and this bar is subjected to a tensile force, or like you handling a stick or a bar and you applying a tension over it. So this tension will result into some extension increase in the length, and the diameter of this stick or bar will be slightly decreased. So if you are applying a tensile force over this bar, this tensile force will produce a stress. What is the type of this stress? It is normal stress. So again, we said that from once we started this lecture, the force will produce deformation. Also, it will produce strain. It will produce stress. All of them are results of the applied force. But the most accurate one that describes how the object is severely affected by the force is the stress. So that's why here we are discussing and focusing more over the stresses. Make sense? So the force, if it is tensile force, that the tendency of this force is to stretch the bar, stretch the object. So it will produce a stress. What is the type of this stress? It is a normal stress. The same thing if this force is, the tendency of the force is to compress. So applying a compression, bracing over the object with the tendency to decrease the length of this object, and as a result the diameter will slightly increase, as already shown here in this sketch, that this guy, he is applying a compression over the object. This compression will produce, so the compression, it is a force. This is just you're pushing over the bar. This is a force. This force somehow can be converted or also can be used for the calculation of stresses, a stress acting over this stick or bar. So the stress that is going to be produced because of this compression force, it is still a normal stress. The same thing, if you have a stick and instead of stretching or compressing the stick, you just bending it. Like you do have this bar and you try to apply a bending over it. So the bending will result in some curvature into this bar. This bending also will produce a stress. What is the type of this stress? It will be also normal stress. So the normal stress produces because of three actions. Either tension or compression of a bar or bending of a bar. Make sense? But the other type of the stress, which is the shear stress, it produces because of twisting or shearing. So again, the normal produces because of tension or compression or bending of a bar. But the shear stress produces of twisting. So what is twisting? Like you do have this bar and you try to twist the bar. Give it a twist. So this twisting action, as already shown here, this produces a stress. What is the type of this stress? It is a shear stress, not a normal stress. The normal stress doesn't produce because of a twisting. The twisting produces a stress. The type of this stress will be a shear stress. Make sense? The same thing like the screwdriver. Like if you are using the screwdriver to screw this bolt into anything, into a wall or something. So when you try to screw it means that you're gonna rotate. This rotation, it is twisting. It is a form of twisting. How it is twisting? Just to understand this twisting thing, somebody gonna say, okay, this is just rotation, right? Because you are rotating. Yes, I'm rotating. But within this bar, within this body of the screwdriver, there is some twisting happening. It is too small that you cannot observe by the naked eye, but it is there. And that's why this body of the screwdriver is subjected to some twisting or subjected to a shear stress. This twisting produces a shear stress into this body of the bar. To understand it more, imagine or assume that this body is made of plastic. And this screwdriver, it is made of steel and very tough, very strong screw. But the body of the screwdriver itself, it is made of plastic. And you just try to use it to screw this bolt. If you try to give it rotation, what should gonna happen to this bar? The screw won't gonna be rotated. The screw is very strong, but the body of this screwdriver, it is very weak. It is made of plastic, rubber material. So if you try to rotate, and instead of rotating the screw, the thing that it will be twisted, you're gonna see and observe the twisting into this body, right? So this means that there is some twisting happening into the body of this bar. This twisting will produce a stress. This stress is known as a shear stress. So one of the forms or the reasons of making a shear stress is the twisting to any object. The other thing is the shearing. This shearing action, that's why we got the name of this type of stress as shearing. Shearing, it means that, like this case, assume that this is a bolt or a pin or a stick, and these are two plates. So this pin is just used to support these two plates, and you try to slice one to the other one. And assume that these two plates, these two strips or plates are very strong, but this bar in the middle, this pin in the middle, it is the thing that is going to fracture. The thing that is going to be broken down. So what's going to happen once you stretch or move very strong, you apply very high force, this bar, it will be sliced, like you slicing something. So this action is known as shearing. Like, for example, you do have a piece of cheese and you just slicing it, right? So this slicing, you're going to end up with like multiple slides. So this action, the movement of the knife, this is a shearing over this surface. So this is a shearing action, like you cutting something twice. So this cutting action or shearing action produces a stress over this part. This stress is known as a shear stress. It could be not understood to many of you, the shearing effect, but also you can, anyway, just to understand, there is the slicing thing, like you using two scissors and you cut a piece of paper over the very thin thickness of the paper. There is a stress that is going to be produced, and that's why it had been cut. This stress is known as a shear stress, comes because of the shearing action, the cutting action of the scissors. So it is like you to have multiple layers, like in this figure here, in this representation, like you to have multiple layers, 3 layers, and you try to slide one layer with respect to the other layer. So like one layer is gonna move to the right, one layer is gonna move to the left. So this will result in some kind of shearing. This process, this like a friction, assume that there is a friction between these two. Definitely there should be delamination or friction between these two layers. But anyway, one layer is gonna move to the right, the other is gonna move to the left. This type of movement or this type of action is known as a shear. This shearing or cutting will produce also another type of stress known as the shear stress. So in general, we have two types of stresses, either normal stress or shear stress. The normal stress produced because of 3 things. Either tension, compression, or bending. But the shear stress produces because of 2 things: twisting of objects or shearing objects. Make sense? So these are the different types of the stresses. Now let us discuss how we can calculate the normal stress and the shear stress. Remember that this is the subject of the mechanics of material class. After 2 years or something, you're gonna study this course with more detail and so many applications about the calculation of all the forms of normal stresses, all the forms of shear stresses. But here, I'm just gonna give you the simplest equations and relations for calculating the stresses from a force. Remember that the stress, it is something that is produced because of an applied force. So the question is, how the stress could be related to the force? This depends on the type of the stress, and this is the subject of the mechanics of material class, as I mentioned. But here, I'm just going to show you how we can calculate the stress due to a tensile force or a compressive force. So these are the things that we're going to consider here for some simple applications, but this part will not be covered. We won't gonna discuss, I will not explain to you or show you the relation how we can calculate the stress due to bending moment. Why? Because it needs so many details. And anyway, this will be covered in the mechanics of material class. The same thing here. I'm just gonna show you how we can calculate the shear stress due to the direct shear, due to the shear effect. Due to the shear, not due to the torsion. This part will not be covered in this course. But anyway, it will be explained with more details in the mechanics of material class. All right? So how we can calculate the normal stress due to tension or compression. Remember, I will not show you how we can calculate the normal stress due to bending. Make sense? So it is very simple relation. Like you don't have an object like this bar, it is subjected to a tensile force, or this bar, the same bar, but it is subjected to a compressive force. No matter what this force, it is tension or compression. If you divided the force by A stands for area. So this is the cross-sectional area, and I'm gonna explain to you what is this cross-sectional area. This is gonna give you the normal stress due to this force. So again, as we discussed here, we said that the normal stress produces due to a tensile force or a compressive force over a bar. So if you have a bar or a stick that is subjected to tension or compression, these forces will produce normal stress. How much it is? So the normal stress due to this force will equal to the F over A. Very simple expression. Plus or minus, what is this sign? It could be positive, it could be negative. It means that this stress could be positive stress or it could be negative stress. Depending on what? Depending on what the function of the force. This force, is it tension or compression? If it is tension, so it should be positive. If it is compression, it should be negative. So the sign here indicates the type of the stress. Is it positive? It means tensile normal stress. So we're going to say that we're going to name it as tensile normal stress. If it is negative, it will be compressive normal stress. So the sign indicates whatever it is, tension or compression. It is a normal stress. Both are normal stresses, yes. But it is due to tension or compression, it will be different. So that's why we are incorporating or adding the sign here. Make sense? What is the force? It is the external force, which in many cases will be given to you. But the question is, what is the area? The area, this is the cross-sectional area that is subjected to the force. Or in other words, to be more accurate, that's why we got the name normal stress. From where did we get this name of normal stresses? Because the normal stress, according to this direct tension and compression, this is the stress that is going to be produced due to a force F that is acting over a surface area, and this area should be normal to the force. So that's why we got the name normal. Normal, it means perpendicular. Like for example, let us assume this bar that is subjected to this forces F. This force F, both sides, it means that it will be stretched with a force F. And assume that this bar for some reason will be sliced or will be fractured, and there will be an area. So this is the area that I'm talking about. As you can see, the force F, it is perpendicular to the area. The area behaves like it is like a surface. This surface, if I ask you what is the normal to this surface, in 3 dimensions we do have 3 axes as x-axis, y-axis, and z-axis. So it means that any surface, whatever it is, it has only one normal, one direction that is perpendicular to it. This x-axis, it is parallel to the surface. This y-axis also, it is parallel to the surface, but we don't have a normal, only one normal, which is z-axis to the surface. So this force, as already shown here, it is perpendicular to the surface, normal to the surface. So that's why this force will produce a normal stress. So again, any force that is perpendicular to the surface will produce a stress. What is the type of this stress? It will be a normal stress. How we can calculate it? This normal stress sigma equals plus or minus whatever it is projected out of the surface, indicating that this is tension, so it will be positive. But if this force is going to the surface, it will be compression. Like for example, we may have another object like this one, pillar, that something that is fixed into the ground, and it is standing vertical, and this is the surface that I'm talking about. And for some reason, this surface, it is subjected to a force. But this force goes into the surface. It is normal to the surface, yes. Perpendicular to the surface, yes. But it is going into the surface. It means that this force will be compression force. It means that the stress due to this force will be negative. Why negative? Because it is going into the surface. The force divided by the area. Which area? This is the cross-sectional area. Your objective is just to calculate the area of this circle and put it into the denominator. You're going to end up with the stress due to that force. But if the force it is projected out of the surface, it will be positive, indicating that it is tension. So that's why you're going to end up with a tensile stress that is equal to positive F over A. A, this is the cross-sectional area of this square area. Make sense? So this is simply how we can calculate the normal stresses. Whatever it is, tension or compression due to a force that is acting, the condition is that this force should be perpendicular or normal to the surface. So that's why we got the name as normal stress. Alright, so if this is the normal stress, how about the shear stress? How we can calculate it? The same thing, almost the same expression. So the shear stress, which we're gonna give it a symbol as tau. So the symbol for the shear stress, it is tau, but for the normal stress, it is sigma. This is what we use. But anyway, both are stresses, but two different forms and types of the stresses. One is normal, the other one is shear stress. Just to distinguish the normal stress from the shear stress, the normal stress will be given the symbol sigma, but the shear stress will be given the symbol tau. So this is the tau, which is the tau, this is the tau, which is TAU. This stands for the shear stress, just to distinguish the normal stress from the shear stress. So the tau, it's gonna be F over A. Or in some cases, it could be F over 2A. So forget about F over 2A, we're gonna discuss this later. But as you can see, even the expression for the shear stress, which is tau, or the normal stress, which is sigma, both are having the same expression, F over A, the force over area. But here the thing is that I didn't include the positive or negative sign because it requires lots of investigation, which is not the subject of this course. Anyway, this will be discussed, as I mentioned, with more detail in the mechanics of material class. So that's why I'm not specifying the sign. So here we were not going to consider the sign for a shear stress, but definitely we have to consider for the normal stress. Why? Because in the normal stress, it is not a big deal. If the force it is tension is going to be positive, if it is compression, it's going to be negative. But here, don't consider the sign or give a sign to the tau. I'm not specifying the sign. Why? Because as I mentioned, this requires lots of investigation and procedure to identify this sign, which will be covered in the mechanics of material class. Make sense? But still we are using the same expression. Despite the expression is the same, this area term is different from the normal to the shear stress. How? For example, we're still using the same area, force over area, the same expression, but the area is different. Let us, just to explain it to you, let us consider the example of the pillar that I just explained. We said that assume that you do have this pillar that is already fixed on the ground in this way, okay? And let us assume that in this case, this pillar, it is subjected to not just one force, and instead it is subjected to two forces. One of the forces, it is normal to the surface as F1, and the other force, for some reason, it is parallel to the surface. Like we do have two forces acting over this bar in this direction, that this is F2. So as you can see, this force F1 it is normal, perpendicular to the surface, but the force which is F2 it is parallel to the surface. Like this is the surface and F2 it is coinciding to the surface, over the surface. So we're gonna say that this F2 it is parallel to the surface, but F1 it is perpendicular to the surface. So these are two forces acting over the same area. Yes, two forces acting over the same area. The area is just the cross-sectional area. Calculate the circular area of this circular cross-section of this pillar or this bar. Make sense? So the question is, this F1 will produce a stress. What type of stress that this F1 is going to produce over this pillar? It will be normal stress. Why normal stress? Because the force F1 it is perpendicular to the cross-section. So this F1 will produce sigma that we discussed before, using the same expression, F over area, the same area, right? But the F, it will be F1. So the normal stress will be tension. Why? Because it is positive. It is projected out of the cross-section, coming out of the cross-section, F1, which is the force divided by the area. This is what we explained. But this F2 will produce a shear stress, not a normal stress. Why? Because it is parallel. So again, the shear stress, it is produced because of a force acting over a surface, but the condition is that this force should be parallel to the surface. But if it is normal, it will produce normal stress. Very simple. So the shear stress will produce due to any force acting over any surface, but the condition is that this force should be coincident to the surface, should be parallel to the surface, like F2. So F2 will produce shear stress, will produce tau. It will not produce sigma. Equals F2 divided by the same area. Remember that we're still using the same area, but the condition is different. The force here, F1, it is normal, produce normal stress. F2, it is parallel, produce shear stress to the same cross-sectional area. Make sense? So this is simply how we can distinguish between normal stress and shear stress. And as I mentioned, this normal stress producing case that you do have slicing, because the tendency of F2, for example, is to slice the surface. So that's why it should be parallel to the surface. That the direction of the force, it should be coincident and parallel to the surface over which you're slicing the object. Like for example, in this case, you do have two pieces and they already sticking together through this adhesive material or adhesion. And you are applying some force over this bar. So if this force is strong enough, this part, this piece will be sliced down. It will be stretched down, moved down, not stretched. It will be entirely moved down, cutting this adhesion or this adhesive material that is already used for holding or joining these two pieces or parts together. So this is a kind of a shear stress, but this shear stress, it is known as single shear. This type of stress here, this type of stress is known as single shear. What does it mean, single shear? Because the slicing will take place over only one section, one side of this plate, which is this side, for example. But it will not be happening over the other side, over the other surface. But in this case, this is another example that indicates that we do have double shear. Double shear, it means that this adhesive material will be sliced twice from this side and that side. So this shearing, it will be happening twice over the two surfaces. So that's why we got the name as double shear. This is a single shear case, but this is a double shear case. So it means that if the slicing in general, if the slicing is going to happen over one single surface, it means that this is a single shear. But it's going to if it's going to happen over two surfaces, it will be double shear. The question is, can we do have triple shear or more? We can, but it is not a normal case. Normally or usually we do have only single or double, but there are some special scenarios that we can have triple and fourth and so on. It means that the number of the shearing surfaces could increase more than double, but as I mentioned, these are in some special cases, but generally we can consider that we do have either the single shear or double shear for now. Like for example, in this case, this bolt itself, it will be sheared. How? Assume that this bolt is made of glass. You want to just imagine this shear thing, assume that it is made of glass. Glass, it is a very brittle material. What does it mean brittle? It can be easily fractured. So if you try to move this plate A, so this bolt, it is used on holding two plates. Like you do have one plate and another plate, and there is a bolt between them that fixing them together. So what we are trying to do is that I'm trying to move this plate to the left and this plate to the right. So this will result in a shearing. This is shearing action, as I mentioned, right? Over this surface, over the contact surface between them, there is a shearing action. Assume that this bolt is made of glass and it can be easily broken. So once you try to move these two blades apart, this bolt will be fractured over this surface, will be sliced directly, will be broken directly over this surface. So, but it means that the slicing surface or the cutting surface will be only one surface. So that's why this is a single shear. But how about if we have the same bolt? The same bolt. Here we are using two bolts, but this is not related to the number. The double or single shear is not related to the number of bolts. It is related only to the number of sections over every bolt. Even we could have only one bolt, we can remove this bolt, we're still having a double shear. So the double shear, it is not related to the number of bolts. It is related to the number of the sliced sections. Here we had only one slicing section or cutting section. Here we had two cutting sections. So that's why we got double shear. Here in this case, if I assume this bolt, it is made of glass, and this plate will be moved in this direction, this one will be moved this direction, but this one will be moved in this direction. So it means that there should be slicing happening to this bolt. So this bolt will be sliced twice, one over this section and another slice over the other section. It means that the thing in the middle will be rigidly sliced, moved, cut off the rest of the bolt. So we're gonna end up with two sections cut. Not just one section, two of them. So that's why this type of shear will be double shear in that case. So what is the difference in this expression between single shear or double shear? For a single shear, the tau or the shear stress will be the force divided by one area. But why one area? Because it makes sense. We are slicing from one area. But in the double shear, you're just gonna divide by two areas to double the area. Why double the area? Because we are slicing over two areas or two sections, so we have to count the area of this section twice. Make sense? So this is the difference between the single shear and double shear, and this is how we can calculate the shear stress in comparison to the normal stress. It is important to understand that the normal stress produces because of a force that is normal to the cross section, but the shear stress produces due to a force that is parallel to the cross section. Make sense? So the last thing that we're going to mention here is the unit. What is the unit of the stress as we calculate it? So whatever it is, normal stress or even shear stress, we mentioned that the shear stress, it is force over area. The same thing for the normal stress, it is force over area. So what should be the unit? We knew from the previous lectures that the force, it is in Newton, in case that we are working with the SI unit system. With the US unit system, the force, it should be in pound. This is the conventionally what we are defining the force. It would be either Newton or pound in the US system or the international system. How about the area? The area, it should be like millimeter square, centimeter square, is something squared. Why? Because like the area of the circle, it is pi over 4 diameter square. So the diameter, it could be in millimeter, centimeter, inch, and foot squared. So it will be squared. It means that the area, it would be like millimeter square, for example. And this is in the SI system. In the US system, it will be inch square. Or it could be centimeter square, meter square. Here it would be inch square or foot square. Make sense? But this is what we conventionally define the area as millimeter square and the inch as inch square. So how about the stress? Whatever it is, normal stress or shear stress, what should be the unit? According to the definition of the stress, it is force divided by area. So the same thing should be applied to the unit. It would be force, which is Newton, divided by area, which is millimeter square. If we are working in the SI system, if we are working with the US system, it will be bound, because the force here is bound, divided by the area, which is inch square. Make sense? So this is simply the unit of the stress in the US system and the unit of the stress in the international system. Newton over millimeter square. This is what we conventionally define. How about if you define the area as meter square? So it will be Newton over meter square. If you define the force as kilonewton, so it will be kilonewton over millimeter square or meter square. So it means that your objective is just to divide the unit of the force as you dealing with it in the problem by the unit of the area as you already got it in the problem. Make sense? This is gonna give us Newton over millimeter square or bound over inch square. For example, if we are dealing with the area as foot square, so it will be bound over foot square in the US system. If we are dealing with the area as meter square, it will be Newton over meter square. Also, it is important to understand some of the conversions of the units. Like for example, this case. You should understand that the Newton, this is very important. Newton over meter square, it is equivalent to Pascal. This term, this unit is known as Pascal as defined by him for the pressure. So it is Newton over meter square, it is equivalent to Pascal. This is bound over foot square, but we can convert to bound over inch square. Bound over inch square is equivalent to bound per square inch, which is PSI. PSI stands for pound per square inch, which is bound over inch square. It means that this term, we can write this unit as PSI. Also, the Newton over millimeter square, it is equivalent to megapascal. The megapascal, this is the equivalent. This is the 10 to the power 6 Pascal. Make sense? So, if in case that you got it as Newton over meter square, you can simply write Newton over meter square, or you can write it as Pascal. Both the same. If you got it Newton over millimeter square, you can write it Newton over millimeter square or megapascal. Both are the same. If you got it bound over inch square, you can write it as bound over inch square, or you can write BSI, which stands for bound per square inch, which is also equivalent to bound over inch square. Make sense? This table includes the conversion from PSI to the KSI. KSI, it is like kilo PSI. That's why the unit system in the American unit system, it is kind of tricky. So the KSI, it is equivalent, you could understand it as kilo PSI. You can understand it this way. And we mentioned that the kilo, it is equal to the 10 to the power 3 PSI. So we're going to say that the KSI, this K here stands for kilo. This is a prefix. SI, this is like the PSI. You got it like square inch. So it is like kilo pound per square inch. And instead of pound per square inch, which is PSI, so this is going to be like the kilo PSI. So it means that the KSI is equivalent to the 10 to the power 3 PSI. This is something that you should understand. Also, you should understand that the mega here, that the mega Pascal, it is equivalent to the 10 to the power 6 Pascal. Okay, for example, the 1 mega Pascal, it is equivalent to 10 to the power 6 Pascal, because Pascal, it means that you should get rid of the M. To get rid of the prefix, as we discussed the unit, it means that you're going to multiply by its value, which is 10 to the power 6. So it means that the megapascal is equivalent to 10 to the power 6 Pascal. Make sense? How about if it is gigapascal? You can convert the gigapascal into mega. So it will be 10 to the power 3 megapascal, because you're going to get rid of the giga, of the G. You're going to multiply it times 10 to the power 9. Then you're going to add the mega, which you're going to divide by 10 to the power 6. So 10 to the power 9 divided by the 10 to the power 6, this is going to give you 10 to the power 3 as a difference because of the division. So that's why we said that the gigapascal is equivalent to 10 to the power 3 megapascal. Make sense? So these units are important to acknowledge them, and you're going to deal with them the same way as we discussed the units over the previous videos. But again, it is force over area, which is force over length square. This is the unit for this stress, whatever it is, normal stress or shear stress. Make sense? Also, how about the strain? We defined here the strain into this expression. We said that the strain, it is delta, which deformation, and this delta, it is increase in the length. So this delta, it could be millimeter, it could be centimeter, it would be inch, it would be anything. It is a length divided by another length. This L, this is the original length, and its unit, it is millimeter. So the strain, if you divide millimeter by millimeter, you're gonna end up with new units. So that's why this is known as dimensionless. Dimensionless, it means has no unit. So the strain, it is dimensionless. Dimensionless, it means has no unit. Like for example, delta, it could be in millimeter, L will be in millimeter. So millimeter will be cancelled with millimeter. So you're gonna end up with no unit. It means it is a dimensionless, has no unit. So generally speaking, the strain has no unit. Whatever is the unit of delta, if it is inch, you have to make L inch. So inch will be cancelled with inch. Foot will be cancelled with the foot, and so on. So you're gonna end up anyway with no unit for the strain. So the strain has no unit, but the stress has a unit, and this unit of the stress, it is force equivalent to force per length square, like Newton over millimeter square or meter square or pound over inch square. Make sense? So these are for the unit, and that's it for today's video. The objective here is just to explain to you what does it mean stress, what are the different and how it would be related to the strengths, and what are the different forms and types of these stresses, normal and shear stresses, and how they can be generated. This is the objective, and how the stress could be related to the strain through the Hooke's law, and how the strain could be related to the deformation. We understood what is deformation is, what is the strain, what is the stress, and the difference between them. All right, so this is what have been covered over this today's video, and that's it for today, and thank you, and see you in the next meeting.